Hi students, in today's session we are going to discuss beta decay and gamma decay. Beta decay is a process by which the nucleus alters its composition to become more stable. In beta decay, beta particles are emitted which are identical to electrons. That is, a beam of electrons are emitted. Beta decay had several puzzling aspects. That is, the conservation principles of energy, linear momentum, and angular momentum are all apparently violated in beta decay. അതായത് ബീറ്റ ഡീക്കേ എന്ന് വെച്ചാൽ ഒരു അൺസ്റ്റേബിൾ ന്യൂക്ലിയസ് ബീം ഓഫ് ഇലക്ട്രോൺസ് പുറത്തു വിട്ടുകൊണ്ട് സ്റ്റേബിൾ ആകുന്ന പ്രോസസ്സാണ് ഡീക്കേ പ്രോസസ്സാണ് ബീറ്റ ഡീക്കേ. ഈ ബീറ്റ ഡീക്കേ കണ്ടുപിടിക്കപ്പെട്ടപ്പോൾ അത് ലോ ഓഫ് കൺസർവേഷൻ ഓഫ് എനർജി, ലീനിയർ മൊമെന്റം ആൻഡ് ആംഗുലർ മൊമെന്റം ഇതിനെല്ലാം വയലേറ്റ് ചെയ്യുന്നതായി അല്ലെങ്കിൽ ഇതൊന്നും ഒബേ ചെയ്യാത്തതായി കാണപ്പെട്ടിരുന്നു. സോ ലെറ്റ് us see how beta decay the law of conservation of energy is violated, how the law of conservation of linear momentum and angular momentum are also violated initially or apparently. So the violation of energy conservation. The maximum energy of the emitted electrons or the beta rays must be given by E max equal to m0 c square, the rest mass, plus kinetic energy maximum, that is maximum kinetic energy of the emitted electrons. And this energy must be equal to the energy equivalent to the mass difference between the parent and the daughter nuclei. The parent nuclei before beta decay and the daughter nuclei formed after beta decay. So, the maximum energy of the emitted electrons must be equal to the energy equivalent to the mass difference between the parent and daughter nuclei. But it was found that the emitted electron was never found with this predicted kinetic energy maximum. That means there is some missing energy. So where does it go? This led to a violation of conservation of energy. Next, how in beta decay the law of conservation of linear momentum was violated. When the directions of the emitted electron and the recoiling nucleus are observed, they are never exactly opposite as required for linear momentum to be conserved. So for linear momentum to be conserved, if the emitted electron is in this direction, then the recoiling nucleus must move exactly in the opposite direction. But here the directions were not exactly opposite, showing that law of conservation of linear momentum is also not conserved. This is the recoiling nucleus, that is the daughter nucleus which has recoiled after the emission of electrons. Now, both the direction of the emitted electron and that of the recoiling nucleus must be exactly opposite for conserving momentum. But here they are not found to be exactly opposite. That means momentum is not conserved. Next, the spin of this was predicted to be the equation for beta decay, that is the neutron getting changed to a proton and an electron. Now we know that neutron, proton, electron are all fermions with spin half. So in beta decay, on the left hand side or on the reactant side you have just the neutron with spin half, whereas on the product side you have proton and electron. Both these particles have spin half each. That means on the reactant side it is simply spin equal to half, whereas on the product side it is half plus half equal to 1. That means spin is also not conserved, or the spin angular momentum is also not conserved here. So all these conservation laws were apparently violated. In the first look you feel that all of these laws are violated in beta decay. It was then that in 1930, Pauli proposed a desperate remedy. Without any other option, he just put forward a desperate solution to this problem. He suggested that if an uncharged particle of zero rest mass and spin half is emitted in the beta decay together with the electron, the above discrepancies can be solved. അപ്പോൾ 1930-ൽ നിവൃത്തിയില്ലാതെ പൗളി ഒരു സൊല്യൂഷൻ ഇതിന് മുന്നോട്ട് വെച്ചു. പൗളി പറഞ്ഞു ഒരു ഈ ബീറ്റ ഡിക്കയിൽ പ്രോട്ടോണും ഇലക്ട്രോണും ഒപ്പം ഒരു അൺചാർജ് പാർട്ടിക്കിൾ അതിന് സീറോ റെസ്റ്റ് മാസ് ആയിരിക്കണം, സ്പിൻ ഹാഫ് ആയിരിക്കണം. ഇതിന് വിത്തൗട്ട് എനി ചാർജ് ഈ ബീറ്റ ഡിക്കയിൽ ഇലക്ട്രോൺ ഒപ്പം പുറത്തു വരികയാണെങ്കിൽ ഈ മേൽ പറഞ്ഞ ഡിസ്ക്രിപ്പൻസികളെല്ലാം അല്ലെങ്കിൽ വയലേഷൻസ് എല്ലാം തന്നെ സോൾവ് ചെയ്യപ്പെടും. The particle was later discovered by Fermi and it was called neutrino. ഇത് പിന്നീട് ഈ പാർട്ടിക്കിൾ ഡിസ്കവർ ചെയ്യപ്പെട്ടു. അതിനെ ഫെർമി ന്യൂട്രിനോ എന്ന് വിളിക്കുകയും ചെയ്തു. ദ ലിറ്റിൽ ന്യൂട്രൽ വൺ എന്നാണ് അതിന്റെ അർത്ഥം. Then how did the discovery of neutrino solve all the discrepancies related to the conservation laws? ഈ ന്യൂട്രിനോ എങ്ങനെയാണ് ഈ കൺസർവേഷൻ ലോയുമായി ബന്ധപ്പെട്ട പ്രശ്നങ്ങളെല്ലാം സോൾവ് ചെയ്തത്? First, the law of conservation of energy, the neutrino would carry off an energy equal to the difference between the kinetic energy maximum and the actual kinetic energy of the electron. അതായത് നമ്മൾ നേരത്തെ പറഞ്ഞു ഒരു പ്രിഡിക്റ്റഡ് വാല്യൂ ഓഫ് ദി കൈനറ്റിക് എനർജി ഓഫ് ദി ഇലക്ട്രോൺ ഉണ്ട്. പക്ഷെ യഥാർത്ഥ ഇലക്ട്രോണിന് അത്രമാത്രം കൈനറ്റിക് എനർജി കാണപ്പെടുന്നില്ല. അപ്പൊ ആരാണ് മിസ്സിംഗ് എനർജി കൊണ്ടുപോകുന്നത്? ഇറ്റ്സ് the neutrino, the kinetic energy of the neutrino. So the neutrino would carry off an energy equal to the difference in kinetic energy between kinetic energy maximum and the actual kinetic energy of the electron. Then how is the problem of linear momentum solved? The neutrino's linear momentum, direction of linear momentum exactly balances uh, uh, with those of the emitted electron and the recoiling nucleus. അതായത് ന്യൂട്രിനോ ഉണ്ടെങ്കിൽ recoiling nucleus goes in this direction and the neutrino goes in this direction, so that the effective direction is something like this, which is exactly opposite to that of the emitted electron. So the problem of linear momentum is also solved. Next, how is the law of conservation, the spin conserved? Spin conserved means together with the proton and electron, a spin half particle is also emitted. So this neutrino is of two types, neutrino and antineutrino. So one has spin plus half and the other one with spin minus half. So the problem of spin conservation is also solved. So plus half for neutron, plus half for proton, plus half for electron, and minus half for antineutrino. So the problem of spin conservation is also solved. So based on all these things, two kinds of neutrinos are involved in beta decay. This is what I told you just now. That is neutrino and antineutrino. One with spin half and the other one with spin minus half. What we call the ordinary beta decay. In the ordinary beta decay, antineutrino, new bar is emitted. That is neutron getting converted to proton and electron with the release of antineutrino. So here neutron has spin half, proton spin half, electron spin half, and the neutrino spin minus half, so that spin is conserved. This is called negative beta decay. That is neutron getting converted to proton, electron, and antineutrino is called, which is what we call the ordinary beta decay, is actually negative beta decay. The second type of beta decay is a proton getting converted to a neutron, positron, and neutrino. Proton is getting converted to neutron, positron, and neutrino. Proton has plus charge, neutron has zero charge, positron has plus charge, neutrino has zero charge. So again, the law of conservation of charge is uh, maintained here. So this is the second type of beta decay, and it is called positive beta decay or positron emission. And the third type of beta decay, there are three types of beta decay. First one, negative beta decay. Second one, positive beta decay or positron emission. And the third one is the proton captures an electron and it gets converted to a neutron and a neutrino. Neutron and neutrino. This is electron capture. Proton capturing an electron and becoming a neutron and neutrino. These are the three types of beta decays. Now, the neutrino hypothesis was completely successful. Neutrino was discovered very much later because its mass is either zero or it has a mass equivalent of a very few electron volts, that is a very small mass. Lacking in charge and mass, the interaction of neutrino with matter is extremely feeble because it has no. When does matter? When does a charged particle? When does a particle interact with matter? It should have either a mass to interact or it must have a charge to interact, and neutrino lacks both of these. So its interaction with matter അല്ലെങ്കിൽ മാറ്ററുമായിട്ടുള്ള അതിൻ്റെ ഇടപെടൽ വളരെ വീക്കായിരുന്നു, കാരണം അതിന് മാസും ഇല്ല ചാർജും ഇല്ല. സോ ന്യൂട്രിനോ വുഡ് പാസ് ത്രൂ എ സോളിഡ് അയൺ ഓവർ 100 ലൈറ്റ് ഇയേഴ്സ് ബിഫോർ ഇന്ററാക്ടിങ്. അതായത് ഒരു ന്യൂട്രിനോ ഒരു സോളിഡ് അയണിൽ കൂടെ കടന്നു പോവുകയാണെങ്കിൽ ഒരു 100 ലൈറ്റ് ഇയേഴ്സ് ഇസ് എ വെരി ലാർജ് യൂണിറ്റ് ഓഫ് ഡിസ്റ്റൻസ്. അപ്പോൾ 100 ലൈറ്റ് ഇയേഴ്സ് എല്ലാം ഇതിൻ്റെ ഉള്ളിൽ കൂടെ നീങ്ങിയാൽ മാത്രമേ അത് അയണുമായി ഇന്ററാക്ട് ചെയ്യുള്ളൂ. അത്രയും ദൂരം അത് ഇന്ററാക്ട് ചെയ്യാതെ പോവാം. That means the interaction is very weak. So the only interaction with matter a neutrino can experience is through a process called inverse beta decay. ന്യൂട്രിനോ ഒരു മാറ്ററുമായി ഇന്ററാക്ട് ചെയ്യുന്ന ഏക പ്രോസസ് it is called inverse beta decay. So let us see what is inverse beta decay. Interaction with matter means it either gets absorbed or it gets scattered or some kind of transformation or a process should take place. So here in inverse beta decay, this is the equation that take place. This is how the neutrino or antineutrino interacts with matter. That is, absorption of antineutrino is equivalent to the emission of neutrino and vice versa. Absorption of antineutrino is equivalent to the emission of neutrino and vice versa. That means here the matter, the proton in the matter absorbs an antineutrino and a neutron and a positron is emitted. Then a neutron interacts with the neutrino to give proton and electron. These equations form inverse beta decay. അതായത് ഇവിടെ മറ്റിടത്തെല്ലാം നമ്മൾ ഇതുവരെ പഠിച്ച 3 ബീറ്റ ഡികെ ഇക്വേഷൻസിലും ന്യൂട്രിനോയോ ആന്റി ന്യൂട്രിനോയോ ഈ ബീറ്റ ഡികെയുടെ ഭാഗമായി റിലീസ് ചെയ്യപ്പെടുകയാണ് ചെയ്തിട്ടുള്ളത്. പക്ഷെ ഈ രണ്ട് പ്രോസസ്സിൽ ന്യൂട്രിനോയും ആന്റി ന്യൂട്രിനോയും ദേ ആർ ഓൺ ദി റിയാക്ഷൻ സൈഡ്. ദാറ്റ് മീൻസ് ദേ ആർ ഇന്ററാക്ടിങ് വിത്ത് matter here. So proton on absorbing the antineutrino gets converted to a neutron and a positron, and a neutron on absorbing a neutrino gets converted to a proton and an electron. So this is the only process by which neutrino interacts with matter. So inverse beta decays have extremely low probabilities to occur, but ഇറ്റ് ഹാസ് എ നോൺ സീറോ പ്രോബിലിറ്റി. വളരെ ചെറിയൊരു പ്രോബിലിറ്റി ഇൻവേഴ്സ് ബീറ്റ ഡിക്ക് നടക്കാൻ ഉള്ളൂ. പക്ഷെ അതിൻ്റെ പ്രോബിലിറ്റി സീറോ അല്ല, അവിടെ വളരെ ചെറുതാണെങ്കിലും അത് നടക്കാനുള്ള ഒരു സാധ്യത ഉണ്ട്. അതുവഴിയാണ് it was through the inverse beta decay that the presence of neutrino or antineutrino was established. Next, we go on to gamma decay. Gamma decay means an excited nucleus returns to the ground state by emitting photons. Okay, photons of energy, which corresponds to the difference in energy between the excited state and the ground state. That is, H nu is equal to E star minus E. These photons emitted have energies up to several MeV, that is wavelength between 0.004 to 0.4 angstrom, and are called gamma rays. So when an excited nucleus returns to the ground state, it emits a photon whose energy is corresponds to that of a gamma ray. So that is why this decay is called gamma decay. Gamma decay is represented as ZXA star, that is excited state gives ZXA plus a gamma. So there is no change in the atomic number or mass number of the parent nucleus in a gamma decay, whereas in all other processes, alpha and beta decay, the atomic number or mass number, either the atomic number or the mass number or both gets changed, whereas in gamma decay such a change does not take place. So the gamma ray spectrum consists of sharp lines, and this indicates the existence of a number of energy levels in the nucleus. Depending on from which energy level to which energy level is the transition take place, gamma rays of different wavelengths are emitted, and it shows the presence of existence of different energy levels in the nucleus. Now the wavelength of gamma ray is done using the Bragg's method. Now this is an example of a gamma decay. So here first magnesium 1227 undergoes beta decay, and it becomes aluminium 1327, 13 aluminium 27 in its excited state. This excited aluminium returns to the ground state either in this manner, emitting a single gamma ray photon, or it first undergoes a transition emitting a gamma ray of lower energy here, and then it emits one more gamma ray to return to the ground state. Okay, so in both these fashions, the excited aluminium can return to its ground state. Now you have to learn two important definitions. One is, what are isomers? A long-lived excited nucleus is called an isomer. That is an excited nucleus which can remain in the excited state for a long time. So an excited nucleus having a half-life of very large or it has a very large lifetime is called an isomer. So example is strontium 3887 in the excited state has a half-life of 2.8 hours. So it is an isomer of strontium 3887. Another one very commonly asked question in your exam is, what is internal conversion? So an excited nucleus may return to the ground state by giving up its excitation energy or giving that photon of energy to an atomic electron. It will give this photon of energy to one of the atomic electrons, and that electron gets emitted. And this phenomenon is called internal conversion. I think you got it. A nucleus in the excited state returns to the ground state emitting a photon, and that photon of energy is given to one of the electrons in that atom, and the electron gets emitted in this process. This phenomenon is called internal conversion. The emitted electron has a kinetic energy equal to the nuclear excitation energy minus the binding energy of the lost electron. Nuclear excitation energy means the photon emitted by the nucleus, and a part of this energy will be used to overcome the binding energy of the electron to the atom, and the remaining will go off as the kinetic energy of the emitted electron. ഓക്കെ, അതായത് ഒരു ന്യൂക്ലിയസ് എക്സൈറ്റഡ് സ്റ്റേറ്റിൽ നിൽക്കുമ്പോൾ അത് ഗ്രൗണ്ട് സ്റ്റേറ്റിലേക്ക് വരുമ്പോൾ ഇറ്റ് വിൽ ഗിവ് ഔട്ട് എനർജി. ആ എനർജി എന്ത് ചെയ്യുന്നു, ആറ്റമിക് ആ ആറ്റത്തിലെ ഏതെങ്കിലും ഒരു ഇലക്ട്രോണിന് കൊടുത്തിട്ട് ആ ഇലക്ട്രോൺ എമിറ്റ് ചെയ്യപ്പെടുന്നു. ആ ഇലക്ട്രോണിന്റെ കൈനറ്റിക് എനർജി എത്രയായിരിക്കും? ഈ ന്യൂക്ലിയർ എക്സൈറ്റേഷൻ എനർജി മൈനസ് ആ ഇലക്ട്രോണിനെ ബൈൻഡ് ചെയ്യാനുള്ള എനർജിയെ അതിൽ നിന്നും എടുത്തതിന് ശേഷം ബാക്കി വരുന്ന എനർജി ആയിരിക്കും energy of the emitted electron, and this emitted electron is called conversion electron. The process is called internal conversion, and the energy of the emitted electron is called and the emitted electron is called conversion electron. I hope this session on beta decay and gamma decay is clear to all of you. If you have any doubts, please do contact. Thank you.